Hello everyone and welcome to our channel Electrical Exclusive.
In this class we shall explore a new topic, electromagnetism. We know a magnet has two poles. Suppose this is a bar magnet and the two poles are named as North Pole and South Pole. And remember, we can't separate these two poles. Suppose for any reason this magnet is broken into two pieces, then what would happen? Each piece will be a complete magnet. That means, come to the first piece. Here this part will be the South Pole. Now come to the second piece. This part will be the North Pole. So doesn't matter how many pieces the magnet is broken into, and each piece will be a complete magnet having two poles, a North Pole and a South Pole. The North Pole is assumed as a positive pole, whereas a South Pole is assumed as a negative pole. And the most interesting fact is the two poles of a magnet are equal in magnetic pole strength, which is denoted as M. The letter M refers to magnetic pole strength. Let's take two magnets, two bar magnets actually. This is a bar magnet and this is another bar magnet. This is North Pole, this is South Pole. Likewise, this is the North Pole and this is the South Pole. Now come to the first magnet. Suppose the pole strength at North Pole is M1. Then no doubt the pole strength at the South Pole will be the same, that is M1. Why? Because these are the two poles of a same magnet. Now come to the second magnet. If the pole strength at the South Pole is suppose M2, then no doubt the North Pole must possess that same pole strength, which is M2. So what we learned is different magnets having different pole strengths, and the poles of a same magnet must possess the equal pole strength. Now we shall look out the law of electromagnetism. This is the law of electromagnetism. Like poles repel each other, whereas the unlike poles attract each other. We can say this law is very much similar with the law of electrostatics, where we have studied like charges repel each other, whereas unlike charges attract each other. This is a medium in which we shall place two magnets. This is the first magnet and this is the second magnet. These two magnets are placed at a distance d from each other. D is in meter. We don't need to level the poles, because if these two poles are like poles, then they will repel each other with some force, which is F. And if these two poles are unlike poles, then they will attract each other with that same force, which is F. Suppose the first magnet having the pole strength M1 and the second magnet having a pole strength M2. And now we shall try to find the force experienced between these two magnets. That may be the force of repulsion if these two poles are like poles, or that may be the force of attraction if these two poles are unlike poles. So force experienced between these two poles will be F directly proportional to the product of the magnetic pole strengths M1 into M2 divided by the distance square, d square. The unit will be Newton per meter square. Let's further re-simplify this expression, which implies force F is equal to a constant which is 1 by 4 pi mu 0 mu r whole into m1 m2 by d square unit is the same, Newton per meter square. The letter mu refers to permeability. Mu0 refers to the permeability of air or vacuum, whereas mu_r refers to the relative permeability. The permeability of air or vacuum, that is mu0 is equal to 4 pi into 10 to the power minus 7, and the relative permeability, which is mu_r, is equal to mu by mu0, and this mu stands for the permeability of the medium. Now all we need to do is we need to put the value of relative permeability in this equation. It implies F is equal to 1 by 4 pi mu0. We don't need to put the value of mu0 because it will be cancelled out. Instead of mu_r, we shall put the value mu by mu0. This mu0 and this mu0 will be cancelled out into m1 m2 by d square. Still the unit is unchanged, that is Newton per meter square. Now the final equation comes out, F is equal to 1 by 4 pi mu whole into m1 m2 by d square. The unit is Newton per meter square. Let's take a magnet, a bar magnet. Suppose this is the North Pole and this is South Pole, and this magnet is placed in a medium, suppose air medium. Then we can say the space surrounding this magnet will be under stress, and that stressed space is called as magnetic field, and this magnetic field is caused by the magnetic lines of force, which is also called as magnetic flux. The magnetic flux is denoted with the letter phi, and remember the magnetic lines of force or the magnetic flux starts from North Pole to the South Pole, and that's why the North Pole is considered as the positive pole, whereas the South Pole is considered as negative pole, and the magnetic flux is directed from North Pole to the South Pole, and the magnetic flux is measured in Weber. Now we shall find out the magnetic flux density. Which is denoted as B. B is equal to flux, that is magnetic flux, per area. The unit will be Weber per meter square. This is the equation for magnetic flux density. Now we shall find out magnetic flux intensity, which is denoted as H, which is equal to force divided by the flux, that is magnetic flux. So unit will be Newton per Weber. This equation signifies the magnetic flux intensity, and from these two equations you can find permeability, which is denoted as mu is equal to the magnetic flux density B divided by the magnetic flux intensity, that is H. This is the equation for permeability. This is all about the electromagnetism, and now we shall relate the electromagnetism to the electrostatics. Let's do it. The force of attraction or the force of repulsion between two differently charged bodies in a specific medium is F is equal to 1 by 4 pi epsilon into Q1 Q2 by d square, and the unit is Newton per meter square. Likewise, the force of attraction or the force of repulsion between two magnetic poles in a specific medium is F is equal to 1 by 4 pi mu whole into m1 n2 divided by d square, and the unit is Newton per meter square. The electric flux is denoted as psi, whereas the magnetic flux is denoted as phi. The electric flux can't pass through any material, whereas the magnetic flux can easily pass through the magnetic materials such as the magnetic metals. The electric flux is measured in coulomb, whereas the magnetic flux is measured in Weber. The electric flux density, that is beta, is equal to electric flux per area, whose unit is coulomb per meter square. Likewise, the magnetic flux density B is equal to the magnetic flux, that is phi per area, and the unit is Weber per meter square. The electric flux intensity, that is H star, which is equal to the force divided by the electric flux. So the unit is Newton per coulomb. Whereas the magnetic field intensity, that is H is equal to force F divided by the magnetic flux, that is phi. So the unit will be Newton per Weber. From these two equations, we can easily find the permittivity, that is epsilon, which is equal to the electric field density divided by the electric field intensity, that is beta by H star. Come to this side. From these two equations, we can find the permeability, that is mu. Mu is equal to the magnetic field density divided by the magnetic field intensity, that is B by H. The electromotive force, that is EMF, is equal to current I into resistance R. On the other side, the magnetomotive force, that is MMF, is equal to the magnetic flux phi into reluctance, which is small r. Resistance R is equal to rho L by A. Rho stands for resistivity, L is length of the conductor, and A is area of cross section. The reluctance R is equal to L by A mu. L stands for length, A stands for area, and mu is the permeability. To evaluate the other equations, we need to relate the MMF with the EMF. EMF is equal to N d phi by dt. This is one equation. Another equation for EMF is L di by dt. This is the second equation. From these two equations, Li is equal to N phi, which is the value of MMF.
Stay tuned for more videos and don't forget to subscribe our channel Electrical Exclusive, because we promise to provide you the best we can. Thanks for watching.